So we talk about the relativity of velocity. Relativity of velocity. 就是小学的时候啊，我们就是速度就直接相加啊，是速度就直接相加哦，或者是速度直接相减。如果是同一个方向或者是反向的话，那实际上我们学完之后就知道不可能嘛，因为它光速是恒定的，然后你朝着光线走的话，你也看到光速；你反着光的方向走，你也是看到光速，所以不可能是这么简单的相加跟相减。也就是说，这个是 u prime， 这个是 u， 就是在不同两个坐标系上面看到的速度。那这个就是两个坐标系之间的相对速度。So this is actually when a particle is moving with speed u prime in the positive t prime direction, in the positive x prime direction should be x prime direction in the inertial reference frame s prime. That itself is moving with speed v parallel to the x direction of a second inertial reference frame s. So actually, this one is moving. This inertial reference frame is moving. This is relatively stationary. So the speed of u of the particle as measured in s is this one. So compare with the Galilean 就是古典力学的。So the velocity transformation is simply just you add the velocity together. So actually, how do we come up with this one? So actually, we have in table 37.2 we have delta x equals gamma delta x prime plus. So if you just exchange t and t prime, so this sign become positive. So it is there v times delta t prime, something like this, and then delta t would be gamma delta t prime plus v delta x prime over c squared. So we have these two, which is actually these two. Yeah. So actually we just divide them. So we have a delta x over delta t, which equals to gamma and gamma can be cancelled. So we have a delta x prime plus v over delta t prime over delta t prime plus v delta x prime over c squared. So actually this one is nothing but delta is nothing but u, which is the velocity in reference frame s. Velocity in s. So u prime is velocity in s prime. So this is this is u, or maybe you can take delta t tends to 0, something like that. So for the right hand side, we can just divide it by delta t prime, divide it by delta t prime. So so the first one will be delta x prime over delta t prime, and then the second term will be nothing but v, because v delta t prime and delta t prime can be cancelled. And for the denominator, delta t prime divided by delta t prime, so it is 1. And then the next one is plus v delta x prime over delta t prime, and then over c squared, something like that. So this is u, and this one delta x prime and over delta t prime should be u prime, or so this is u prime plus v over 1 plus uv over c squared, u prime v over c squared. So this is this one. Okay. So we have proved this 37.29. Okay, so be careful to substitute the correct sign for the velocity above equation reduced to the classic curve. So yeah. So when we apply the formal test for letting c tends to infinity, in other words, relativity equation is correct for all physical possible speed, but classical equation is approximately correct for speed much less than z, which means that if you take c tends to infinity, and then this term will tend to 0, it will shrink. 37.29 will shrink to this one. So because at that time you consider a speed of light may be infinite, so or if you have a very small speed compared with the speed of light, then you will ignore this stuff. Or you can just assume v over c, u prime over c is much less than 1, or c tends to infinity is similar. Okay, so we have yeah, so okay, I just leave the space here too, but yeah, I'm not sure. Yeah, so actually I've just divided it. Okay, so next, so it's about the Dopplers effect for light. Dopplers effect. So in the for sound, you know the Dopplers effect. Feel like the ambulance is moving closer to you or moving away from you, then you feel like the frequency of the will be the frequency become higher or lower. Depends on if it is approaching you, then you feel like the sound is the frequency will become higher, and if it is moving away from you, then you feel the frequency become lower. and this effect will also appear here in the special relativity. In the special relativity. So when the light source and the light detector move relative to each other, the wavelength of the light as measured in the rest frame of the source is proper wavelength, lambda 0. So the detect wavelength lambda is either longer, a redshift, or shorter, a blue shift. So depending on whether the source detector separation is increasing or decreasing. 那这个看起来啊，就是一个式子嘛，就是你就代公式嘛。那其实这个在物理上啊，或者在宇宙学上啊，是一个蛮重要的东西，就是这个红移现象。就是我们发现啊，就是天上的星星都是偏向于就是红移的现象，绝大部分都是红移。那反过来就是印证说这个宇宙是在膨胀的是在膨胀的，那才会看到这个红移现象。所以如果你有看过那个叫做《时间简史》啊，就是 Stephen Hawking 写的那本，就是他会讲说那个《时间简史》嘛，就是宇宙的什么起源、什么大爆炸之类的。那他说现在啊，以目前为止，现在这个宇宙啊100多亿年嘛好像150几还是160，我忘记了，反正150大概150亿年。那它就一直在膨胀。那宇宙会怎么样结束呢？它有可能一直膨胀到一直膨胀下去。那也有一种可能是它膨胀到一定程度，它就开始塌缩，然后缩回一个基点。但是万一真的是那样的话，也不需要太惊慌，因为它花了100多亿年去膨胀的话，它也需要花100多亿年去塌缩，所以我们等不到那一天。是不是但是到目前为止，我们还是观测到是那个红移现象，至少在上一个世纪，他们就是观测的时候是发现是红移现象红移现象就是波长会变长你就看到这个波长会变长，你远离你的时候波长会变长，然后频率会变低波长会变长，因为它速度是固定的嘛，So where beta equals v over c, and v is the relative radial speed along. If the separation is decreasing, 就是它向你靠近的话，那就是向下反过来啊。So for this case, lambda should be lambda 0 multiplied by this one for this case. So for the speed much less than c, the magnitude of the Dopplers wavelength shift delta lambda is approximately relative to v by this one. V is much. So actually you can see that v over c is delta lambda over lambda 0. If you assume v is much less than c, Actually, you need to use the Taylor series expansion. You need to use the Taylor series expansion to express this monster. maybe not so difficult. Maybe you can just ignore that one in the numerator. So maybe you can just expand this one. It will be better, because if you expand this one, you feel like you have 1 plus beta plus beta square plus dot dot dot, and then you can approximately as this one, and then you further expand it, then you will become 1 plus 1 half. Not right. So this is not like that one. So maybe we still need this term. We still need this term. So 1 plus beta times this stuff will be 1 plus 2 beta plus blah 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 blah. Oh, plus dot dot dot. So in this case, when you expand this one, so you will have 1 plus beta. You will have 1 plus beta plus dot dot dot. So this is the delta. So this is beta equals the delta term. So we have 1 plus beta. So this is delta. Okay. So yeah. So you still need some sort of Taylor series expansion, because this one you still need the Taylor series expansion. Okay, so for the transverse Dopplers effect in the figure source, S move past a detector. So detector is here, and then you are moving perpendicular to it, maybe. So as long as to this point, the velocity of S is perpendicular to the line joining P and D. And at that instance, S is moving neither toward or away from D. If the source is emitting sound wave, the frequency of frequency f sub 0, D detects that frequency with no Doppler effect when it intercepts the wave that were emitted at point P. However, if the source is emitting light wave, there's still Doppler effect called the transverse Doppler effect. In this situation, the detect frequency of the light emit when the source is at point P, so which is like this. So this is another difference between the classical mechanics and the relativistic effect. So for the classical mechanics, we don't need to consider. There are no Doppler effect for the sound wave, but for the light wave, we still need to consider the transverse Doppler effect. So actually, you can just use the Taylor series expansion. You can approximate this one up. If beta is much smaller than 1, then it will be like that. Just like this one is approximately 1 plus 1 half of x. Use the Taylor series extension will help you. So we have, if it is a negative sign, it is negative sign. So we have like this. So here the first term is what we would expect for sound wave. And again, the relativistic effect for low speed light source and detector appear with the beta square term. So it will effect on the frequency of the light. Okay, up till now, any questions? So next we talk about the momentum and the energy. and energy. So just now we have some example about the Star Wars. We talk about very very large scales， 从一个很大的尺度啊，什么星球啊，什么银河系啊什么的。那现在我们就讲到一个很微小的尺度，就是到一个粒子的尺度。So in relativistic mechanics, the definition of the linear momentum is p. So in classical mechanics, we only consider p equals mv. But here, the p we also need to consider the Lorentz factor, the Lorentz factor. So this equation gives the correct definition of momentum for all physically possible speed. So for the speed much less than c, gamma will reduce to somehow like 1 because gamma is this term v over c square. So if v over c is much smaller than 0 or tends to 0 or much less than 1 or tends to 0, then so for c, v and c is much smaller than 1 or tends to 0, then gamma will tend to 1. So it shrinks to this case. So this equation gives the correct definition of the momentum for all physical possible speed. For a speed much less than c reduced to compact an object mass m, and the relativistic and the equivalent energy are related by E0 equals mc squared. So maybe when you are a primary student, you already know this, but you don't know what it really means, actually. So which without the subscript 0 is the best known science equation of all time. This energy E0 that is associated with the mass of an object is called the mass energy or rest energy. So this is the E0. So we have the subscript here. Maybe for primary student we don't have a subscript, so we only have a E 等于mc 平方. So the second name suggests that E0 is an energy that the object has even when it is at rest, simply because it has mass. And if we assume that the object's potential energy is 0, then its total energy E is the sum of the mass energy. So if it is actually moving, so for this one, it is at rest, don't move at all. But for this case, this is the total energy. It consists of the rest energy and also the kinetic energy. But the kinetic energy for classical mechanics, it is 1/2 mv squared. Or in the next chapter, we may use a p squared over 2m. Here maybe this one. But for the relativistic special relativity, the k should be gamma minus 1 mc squared. Oh, this is k. Pretty strange. 所以这个叫做质能方程，就是如果你的质量可以完全变成能量，那个能量就那么大，非常的大，因为你可以想象，这个是质量，这个是光速，所以你如果你整个人都变成能量的话，应该会炸掉整个地球吧，或者是炸掉澳门吧，我不确定能量到底多大。但是如果你考虑那种什么核能啊，或者是原子弹啊，那些就是一些核反应的时候，它比如说铀元素它做那个核裂变， 的时候哦，它就会原子哦，它从一个铀原子哦，它就会射出一个中子，然后它的原子数会下降，那它的质量啊，有一部分就变成能量，所以那个只是差一点点，它就有那个能量，或者是核聚变的话通常是氢原子，或者是原子序比较少的原子，它们从氢原子变成氦啊，氢变成氦嘛，氦就是氢是原子序是1嘛，那氦是原子序是2嘛，那氢变成氦的时候啊，它就会叫做核聚变。核聚变，那这个的能量就比那个核裂变来得更大，但是这个条件就很难发生的，因为如果你要听那个氢弹嘛，就是氢弹的话，它需要一个普通的原子弹提供那个足够的温度，它才会有足够的温度产生那个核聚变的反应。那个核聚变反应的释放的能量就会更大，所以变成说你要有一个氢弹的话，你要先有一个原子弹当它的一个 warm up， 当它的 warm up。所以那个是小小的质量的改变，就会造成很大的能量，所以这个是比较 general 的那个质能方程，就是总的能量是包括那个静止的能量 rest energy 跟那个 kinetic energy。Okay, so actually we have kinetic energy to be E minus mc square, which is gamma minus 1 mc square. Gamma. So an expression for the kinetic energy that is correct for all physical possible speed, including the speed close to c, is given by this one. So actually you can just use the Taylor series expansion. Actually you can know that if V over C is much less than 1, then K will be 1/2 mv squared. You can actually prove it. It is not that difficult, believe me. Actually, you can just expand this one. So if you like, maybe I can have a quick try. So actually this is nothing but 1 over 1 minus beta square. So actually if you just Taylor series expand it, it will become 1 minus beta square over 2. So 1 over 1 minus this one will be 1 plus beta square over 2 square dot dot dot. So if beta is very small, so we can just take this term. So this is gamma. So gamma minus, so we can just take this one and then we ignore the rest. So gamma minus 1 will be approximately beta square over 2, right? So beta is nothing but V square over C square, and then multiply by 1/2. And then here we also have mc square. So c square and c square can be cancelled, so it is 1/2 mv square. So very quick. But as long as you need to remember this one, 1 plus x is 1 plus x over 2, or minus this one, and also this one. But this is actually the sum of a geometric series. So actually you only need to know these two, and then you can be very strong to derive many equations. So the next one is this one. Is this one. We can actually derive this one. So it feels like it is a Pythagorean theorem. It feels like it is c squared equals a squared plus b squared. So actually you can draw a right angle triangle. This side is E, this side is PC, this side is MC squared. Oh. So this is the total, this is the total energy, this is the total energy, this is the rest energy, E0, and this is PC. I don't know PC, what is PC? The momentum times the speed of light. I don't know what it really means. But actually we can use some ways to prove it. Use some ways to prove it. Maybe I show you next week. But actually, so the interpretation for this one is like the right angle triangle. It's like the right angle triangle. Total energy for this side, and then the rest energy, and then PC. So and similarly for this one, suppose this one is theta. Is theta. So so you can see that sine theta is mc squared over E. And actually E is nothing but mc squared over gamma mc squared. So this is nothing but 1 over gamma. So sine theta is 1 over gamma. It depends on which theta you take. But for the other, cosine theta is PC over E. PC over E. So P is gamma MC. No, gamma MV. P is gamma MV, as long as we have this one. P is gamma MV. Gamma MV times C over gamma MC squared. So gamma MC can be cancelled. So it is V over C, which is beta. So we have two equation looking nice. Sine theta equals to 1 over gamma, and then cosine theta equals to beta. So this right angle triangle link up some interesting factor like the gamma, beta, and then this is the total energy, rest energy, and PC. Okay, so maybe we just stop here.